have been looking at two composite systems. By composite systems, I mean a system which is made up of two subsystems. For instance, the oscillator, which had a simple harmonic oscillator along the x-axis and another along the y-axis, if you wish. That total system was a composite system. Yesterday we looked at the beam splitter. Now the beam splitter again has two input ports, and I feed beams of photons through both the input ports and look at the system as a whole and what happens to the system after it passes through the beam splitter. Today I wish to look at another composite system, which is two spins, spin 1 and spin 2. But in general, these need not be spins. They could be any form of angular momentum, and therefore I would be looking at two particles perhaps which have got angular momenta J1 and J2 respectively, 1 and 2 being labels for the particles, particle 1 and particle 2. So now today I will be talking about addition of two angular momenta So there are two systems given by vectors J1 and J2. J1 squared is J1 dot J1, and I can find simultaneous eigenstates of J1 squared and J1z. The one here, as I have mentioned earlier, refers to the fact that we are talking about the first system, one of the two systems. So J1 squared acting on a state labeled by J1 M1 gives me J1 into J1 plus 1 H cross squared J1 M1, and J1Z acting on the state J1 M1 gives me M1 H cross J1 M1. So the commuting operators for the first system are J1 squared and J1Z, and we can have a complete set of eigenstates labeled by J1 comma M1, with M1 taking values minus J1 to plus J1 in steps of 1. Similarly, I have the second system, and here my notation is going to be the following. I have J2, the 2 stands for the second system, and J2 squared is J2 dot J2. We have already seen that J2 as also J1 are vectors under rotations. Once more, I have J2 squared and J2Z as the operators which simultaneously commute with each other for the system 2, and I can write the following. There are eigenstates, common eigenstates, a complete set of common eigenstates of J2 squared and J2Z, and the eigenvalue equation is this. So here we are. Now if these two systems, these two spin states, now if I were talking about spins, if you recall, I would use the notation S1 and S2 to denote the spin of the first system and the spin of the second system. So I could talk of two spin multiplets, for instance. In general, I would like to refer to them as J1 and J2 to show that they could be any kind of angular momentum. that is any kind of generators which satisfy the angular momentum algebra. Now, if I were talking about these two systems 1 and 2 as non-interacting systems, clearly it is obvious that the following operators commute with each other: J1 squared, J1z, J2 squared and J2z commute with each other, because clearly operators corresponding to the first system commute with operators corresponding to the second system. And therefore, if I have to describe the two systems as a whole, I would use the following labels: J1 M1, J2 M2. By this shorthand notation, I mean the following. We have come across this kind of a situation earlier when we discussed composite systems. You will recall that in the case of the harmonic oscillator, we had state labels N1 corresponding to system A and N2 corresponding to system B. Perhaps you would like to call it NA and NB. In the same sense, here I have the following basis states: J1 M1 for the first system and J2 M2 for the second system. There are two J1 plus 1 states here, because M1 can take values minus J1, 2 plus J1 in steps of 1. There are two J2 plus 1 states here corresponding to this system. And therefore, the total number of states, the total number of basis states of the two systems taken together, that is as a composite system, the total number of basis states are 2J1 plus 1 times 2J2 plus 1. Let me give an example. Suppose we were talking about two spin half particles. So, let me call them S1 is half, M1 can take values half and minus half. Similarly, S2 is half and M2 can take values half and minus half. The understanding being this, that S1 squared acting on the state half half, this is little s1, this is an operator, this is M1, gives me half times half plus 1 in units of h cross equals 1, half into half plus 1, half half, and S1z acting on half half is half in units of h cross, half comma half. Similarly, for S2, I have S2 squared acting on the system 2 state half half, gives me half times half plus 1, half half. I could do the following thing. Instead of J1 and J2, I have used S1 and S2, and therefore, I can make it convenient by denoting this by A and this by B, as I did in the case of the harmonic oscillator, to show that system 1 gets denoted by a subscript A and system 2 has gets denoted by subscript B. S2z acting on half half gives me half half half. So, that is the way it is. Similarly, S1z acting on half half A gives me half ket half half A. S2 squared acting on half half B is half times half plus 1, half comma half B, and so on. The notation must now be evident. System 1 has kets with the subscript A here, and system 2 has kets with subscript B. The point is, what are the basis states of the coupled system or the composite system? Well, the basis states of the composite system would be the following. They would be half half of A half half of B, half half corresponding to A, with half minus half corresponding to B, half minus half corresponding to A, with half comma half corresponding to B, and half minus half corresponding to A, with half minus half corresponding to B. So, I have 4 states. System A has 2J1 or 2S1 plus 1 states, which is 2 states. They are half half A and half minus half A. Similarly, system B has 2 states. And the total is 2 times 2, which is 4 states in total. So, these are the basis states of the 2 systems taken as a whole, and I have given you the 4 states here. This is merely an example. In general, therefore, we have 2J1 plus 1 states times 2J2 plus 1 states, and this is going to be the complete set of basis states for the composite system. I could well work with this set of basis states provided there is no interaction between J1 and J2. On the other hand, if there is interaction between J1 and J2, then I could land a problem. It might be wiser to talk about the total angular momentum of the system as a whole and the corresponding third component of angular momentum, because the eigenvalues, the eigenstates corresponding to the subsystems may not be the relevant basis states here. The eigenvalues corresponding to J1 and J2 may not be the good labels to use, and in fact, they need not be conserved quantities because of the interaction. And therefore, it would be more sensible to look at the composite system in terms of the total angular momentum of the composite system and its third component and anything else it commutes with. Now, if I were to talk of the total angular momentum of the composite system, it is clear that it should behave like any angular momentum. It should behave like a vector under rotations, and therefore, like all vectors, the total angular momentum must follow vector addition, and I have j equals j1 plus j2, and therefore, j squared is j1 plus j2 dotted with j1 plus j2, but that gives me a cross term because I have 2 j1 dot j2. Specifically, I should write j1 dot j2 plus j2 dot j1, and that is what I have written here as 2 j1 dot j2. Remember, j1 and j2 commute with each other, they are 2 different systems. Now, suppose I find out the set of operators that commute with j squared. It is clear that for corresponding to j squared, I can have jz, which will commute with j squared. But jz is the third component of the vector j, is a z component of the vector j, and like third components, jz simply adds up. Jz is j1z plus j2z. You could think of j as a specific example, jz ez, and j1 as j1z ez, similarly j2 as j2z ez, and it is clear that jz is j1z plus j2z. That is in a very specific case, but in general, like components of a vector, jz simply adds up, not vectorially, but like scalars would add up. And therefore, the eigenvalue for jz, if I call that m would be equal to m1 plus m2, where m1 and m2 are given there. So, certainly I can talk about j where j times j plus 1 h cross squared is the eigenvalue corresponding to j squared, and m the eigenvalue corresponding to jz, j squared and jz having a complete set of common eigenstates, and m being equal to m1 plus m2. But these are not the only two operators that commute with each other. Look at the following: j squared commutator with j1z. So this is the same as j1 squared plus j2 squared plus twice j1x j2x plus j1y j2y plus j1z j2z. This is j squared, and we wish to find the commutator with j1z. j1 squared certainly commutes with j1z. They have a complete set of common eigenstates labeled by j1 m1. j2 squared commutes with j1z because they are two different systems. But here j1x, j1z do not commute with each other. In fact, they give me j1y. Similarly, j1y commutator with j1z is proportional to j1x. The third term, of course, commutes. So in general, this is not 0. It is not possible for me to find a complete set of common eigenstates of j squared and j1z. But what about j squared and j1 squared? This is all right, because when I expand j squared in this manner, j1 squared commutes with itself, j2 squared and j1 squared commute because they are two different systems, and this is j1 dot j2. j1 commutes with j1 squared and j2 commutes with j1 squared. Therefore, this is 0. Similarly, j squared with j2 squared is 0. So this is what I have. I have a set of operators j squared, jz, j1 squared, j2 squared, all of them commuting with each other. And therefore, if I were talking about the composite system as a whole, and I'd like to talk in terms of the coupled basis. By coupled basis, I mean when you couple the individual systems, perhaps through an interaction, and then I look at the basis states relevant to describe the composite system as a whole. In this case, since these four operators commute with each other, I can label my state as j, m, and of course j1, j2. This would be the manner in which I would label the basis states when I look at the coupled basis. If I were looking at the uncoupled basis, that is where the two spins were not interacting with each other, then I could well use j1 m1 j2 m2. And to get this notation nicely, I would like to call this j1 j2 jm, and so that we may be clear in our minds that this is the coupled basis and that is the uncoupled basis. I would like to draw this thick compared to that which is just single lines, thin lines like that. But since that would be difficult, I am just indicating it by this notation. This notation, it's simply a notation to show that I am now working with the coupled basis, whereas this was the uncoupled basis. I could work with the coupled basis or the uncoupled basis to describe the composite system, which is the sum of two angular momenta, sum within quotations. How we sum up is a different matter. So let us look at the values that j and m can take. I now have the following established. Because we are talking about the coupled state's angular momentum, and therefore I pull out j times j plus 1 h cross squared, j1, j2, jm, and jz acting on this state gives me m h cross So this is what I have, except that because these are angular momentum operators, m takes values minus j to plus j in steps of 1. So there are 2j plus 1 values that m takes, and therefore the total number of basis states for the coupled basis would be 2j plus 1, except that I have to sum over the minimum value of j min all the way to j max in quantized steps, which I have to figure out. So I need to find out the range of values that j can take. Corresponding to each value of j, m takes 2j plus 1 values in steps of 1. J max itself can be found in the following manner. I define something called a stretched case. When m takes the values little j or minus j, I call them the stretched case. So this is the maximum value that m can take for a given j, and this is the minimum value that m can take for the same j. Remember that a j multiplet for a given value of j has 2j plus 1 states with m ranging from minus j to plus j in steps of 1. And therefore, in my example, where I have j1 m1 and j2 m2 as the uncoupled basis states, the maximum value that m1 can take is j1, and the maximum value that m2 can take is j2. And since jz is j1z plus j2z, the maximum value that m can take is j1 plus j2. If m takes this maximum value, clearly j should at least be equal to m, and therefore the maximum value that j takes is j1 plus j2. So in my summation here, j max is j1 plus j2. As an example, suppose I were combining j1 equals half with j2 equals half, j max is 1, and so on. I now have to find j min, but before that I would like to see what is the nature of quantization. What is the next value that j can take in this summation? And that can be simply done as follows. Given j1 m1 and j2 m2, the highest values that m1 and m2 can take are j1 and j2. The next value could be this, because m reduces in steps of 1, and therefore the value that m can take, m is m1 plus m2, could be j1 minus 1 from here with j2 from there. I could have got it the other way. This value could also be j1 plus j2 minus 1 from here, combining with j1 from there. Surely if m takes this value j1 plus j2 minus 1, I could think of the stretched case where j is equal to j1 plus j2 minus 1 and m equals j. That is one manner, that is one way in which m takes values j1 plus j2 minus 1. But I have two states. I have two ways of combining m1 and m2. I have two different choices which will give me the same value of m, and clearly these are two different states. So while one of them can be accounted for by saying that j is j1 plus j2 minus 1, and m as a stretched possibility is also j1 plus j2 minus 1, the other one came from here itself. I started with j max equals j1 plus j2. So what are the corresponding states? j1 plus j2 with j1 plus j2. The next state would be j1 plus j2 with j1 plus j2 minus 1. So that's one possibility, that I start with j1 plus j2 being the value of j, and m reduces in steps of 1. I have 2j plus 1 states in this multiplet, where j is j1 plus j2. The other possibility for m to be j1 plus j2 minus 1 is through this. So the next value of j is j1 plus j2 minus 1. I can argue further. In the next stage, I would look at the following. m1 is j1 minus 2, m2 is j2, m1 is j1, m2 is j2 minus 2. Surely these are possibilities. Then m is j1 plus j2 minus 2. I can also have m1 equals j1 minus 1, m2 equals j2 minus 1. So there are three ways in which m takes values j1 plus j2 minus 2. Surely this can come from j equals j1 plus j2, m equals j1 plus j2 minus 2. It can come from j equals j1 plus j2 minus 1, m equals j1 plus j2 minus 2. And the third possibility would have arisen from j is j1 plus j2 minus 2 and m equals j. That is the same thing, j1 plus j2 minus 2. So I have accounted for all the three possibilities, and these are three distinct states. I go on in this manner, and therefore I realize that j reduces in steps of 1. So j starts with j1 plus j2, comes down in steps of 1, and those are the possible values of j, except that I should now know what is j minimum, and that can be easily found out by arguing in the following manner. In the couple basis, I have summation j minimum to j1 plus j2. Remember, this summation happens in steps of 1 of 2j plus 1 should be equal to 2j1 plus 1 times 2j2 plus 1. And then I can work out, I can do the summation and work out what is j minimum. J minimum is modulus of j1 minus j2. Instead of doing that, I would illustrate this. Again, let us start with j1 is half, j2 is half. So j, the number of states would be 4, because here I have 2j plus 1, that is 2 states. Similarly for j2 I have 2 states. So 2j1 plus 1 times 2j2 plus 1 in my example is 4 states. Now j takes values j1 plus j2. To j min, well, this certainly gives me 3 states. J is 1, m is 1, and these are coupled states. J is 1, m is 0, and j is 1, m is minus 1. That is 3 states. The minimum value is modulus of j1 minus j2, which is 0. That gives me one more state. J is 0, and therefore m is 0. So these are 4 states in the coupled basis, and I have 4 states in the uncoupled basis. So I find that the number of states match, and that is the way it ought to be, quite independent of the kind of basis states that we select. They should form a complete set. Not only that, the number of basis states must be the same in various choices that we make for the basis states. So, let me illustrate this with some more examples. J1 is 1, J2 is half. Recall from whatever was done earlier on spin systems that the value that J can take, in that case you would have called it S, the values would be either integer or half integer positive values in units of H cross. So, I have J1 is 1 and J2 is half. So, J takes values 1 plus half to 1 minus half, modulus of 1 minus half in steps of 1. What are the number of states? In the uncoupled basis, I have states 2j plus 1 states here, which is 3 states here, and that is 2 states there. So, I have 6 basis states. Example 1 1 with half half, or 1 0 with half minus half, and so on. This is J1, this is M1, this is J2, and that is M2. I should account for 6 states here, and that is 2. There are 2j plus 1 states. So, that is for each j there are 2j plus 1 states, and for each j value these are the m values. So, that is 4 states corresponding to j equals 3 by 2, 3 halves, and m takes values 3 halves, half, minus half, and minus 3 halves. So, this is the case j comma minus j, that is the case j comma j, and m comes down in steps of 1. Then I have j equals half. So, that gives me the other 2 states, half half and half minus half, thus accounting for 6 states. So, j reduces from j1 plus j2 to modulus of j1 minus j2 in steps of 1, which is what we have got here, and we have accounted for the basis states. Now, we are in a position to look at addition of angular momenta. The problem simply reduces to this: how do you express a coupled state or a state expressed in the coupled basis in terms of the uncoupled basis? In other words, how do you express 3 halves, for instance, in terms of combinations like this? Or how do you express 3 halves minus half in terms of appropriate basis states there? And that is all that we look at in the context of addition of angular momenta. So, let me look at a simple example combining 2 spin doublets. J1 is half, J2 is half. So, J is 1 or 0, and therefore, the coupled basis states are 1 comma 1, this is J, this is M. Of course, I should write J1, J2, Jm. So, let us do that. Half for J1, half for J2, J is 1, M is 1. So, this is J1, J2, Jm. Then of course, I have half, half, 1, 0, half, half, 1 minus 1, half, half, 0, 0. To begin with, there were 4 states, because it is 2j1 plus 1 times 2j2 plus 1. Now, I have 2j plus 1 states corresponding to j is 1 and 2j plus 1 states corresponding to j is 2. So, this is what I have. I would like to shorten the notation further and not write down j1 and j2 at all. So, this is simply identical to 1 1. This is identical to 1 0. This is identical to 1 minus 1, and this is identical to 0 0. This is a notation. It is a convenient notation. I would like to suppress the indices J1 and the labels J1 and J2 and just keep J and M to represent the coupled basis states. For the uncoupled basis states in this problem, I have J1 is half, J2 is half, that is J1 or J1 M1, J2 M2. So, that is half half with half half. Then of course, I can have half half with half minus half, and then I have half minus half with half half, and I have half minus half with half minus half. Again, I would like to shorten my notation and simply use M1 and M2, remembering J1 and J2 at the back of my mind, just keeping them in my mind. So, I would like to write this state as half half, this as half minus half, this as minus half half, and this as minus half minus half. And these are the uncoupled basis states. So, by way of a shorthand notation, I represent the uncoupled basis set using the labels M1 and M2. I should have written J1 M1, J2 M2, but I am just trying to save some time and write a compact notation for this. So, I write M1 and M2. Similarly, for the coupled basis states, I should have written J1, J2, Jm, but once more I just remember J1 and J2 at the back of my mind, and I keep the labels as J and M. The question that is to be addressed is, how do you write the coupled basis states in terms of the uncoupled basis states? If I were talking about spin, I would talk of the spin triplet when I talk about these, because S is equal to 1, Sz is 1, or M equals 1. S is 1, M is 0, and S is 1, M is minus 1. And I talk of this as the singlet state of spin, because there is exactly one basis state there. So, now let me look at the state 1 0. Well, instead of writing this as 1 0, I could have written this in terms of the uncoupled basis. I would have gotten M equals 0, this is J, this is M. I would have gotten M equals 0 only by using M1 is half and M2 is minus half. So, this would have come from M1 is half, M2 is minus half, but it could also have come from M1 is minus half and M2 is half. So, it should be a superposition. There is no other way I could have used M1 and M2, given the values of M1 and M2. There is no other way I could have produced M equals M1 plus M2 except to combine half with minus half and minus half with half. These are distinct states, and therefore, there is a superposition of these two states to give me 1 0. Suppose I want to find out this coefficient. It is clear that if I did this, that means take the inner product of half minus half with 1 0, that should give me the following. but these are orthogonal states. They have different quantum numbers. Two states are orthogonal, are distinct states if at least one label is different between the two states, and here the M1 labels are different, whereas this is 1 because I have normalized all states to 1, that is the assumption, and therefore A is simply this object. Similarly, B is minus half half 1 0, this inner product is B. Well, this state is a superposition of two of the uncoupled basis states, and we have a way of finding out, as always. We use the same method to find out the coefficients A and B, and since these are normalized states and this state too is normalized to 1, this implies that in general A and B can be complex numbers, and therefore mod A squared plus mod B squared equals 1. The interpretation is very clear. If you expand the coupled basis state 1 comma 0 in terms of the uncoupled basis states half comma minus half and minus half comma half, the coefficients appearing here A and B, when mod squared and added, should give me 1, because after all this state has to be expanded completely in terms of these, and therefore the total probability of it being expanded in terms of these states should be 1. A and B are referred to as Clebsch-Gordan coefficients, or the CG coefficients for short, and they satisfy the following relation. Now, suppose we look at the state 1 1, that is the state out here, 1 comma 1. Let me repeat this. So 1 comma 1 is to be expanded in terms of the uncoupled basis states. The only way by which I could have got M equals 1 is by using M1 equals 1 and M2 equals, M1 equals half and M2 equals half. There is no other possibility. I should have had a half plus half to give me 1, because this gives me 0, that gives me 0, and minus half is minus 1. So when I write 1 comma 1 in terms of half comma half, there is exactly one basis state appearing here and the coefficient is 1. This is called a stretched case. Stretched case because M equals J, M1 equals J1, M2 equals J2. I would say the same thing for 1 comma minus 1, because that could have come only from M1 equals minus half and M2 equals minus half, and that is also a stretched case. So stretched case is this, or M equals minus J, M1 equals minus J1, M2 equals minus J2. When we discuss a stretched case, there is exactly one CG coefficient, and that is 1. That is simply unity. So looked at from the coupled basis framework, the basis state is 1 comma minus 1. In the uncoupled basis, it simply translates to minus half comma minus half. Again, I emphasize that by this object, by 1 comma 1, I mean J1 is half, J2 is half, J is 1 and M is 1. There by half comma half, I mean J1 is half, M1 is half, J2 is half, M2 is half. So whenever M is equal to J or minus J, corresponding to which M1 is plus J1 or minus J1 and M2 is plus J2 or minus J2, it is called a stretched case. So in this problem, I can now write the following. I have 1 comma 1 is half comma half here. This is M1, M2 and this is Jm. 1 comma 0 is A times minus half comma half plus B times half comma minus half. and 1 comma minus 1 is half, minus half comma minus half. These are the stretched cases. We have to find out A and B. Then there is the singlet state, which is 0 comma 0. Again, if m is equal to 0, clearly it could have come from m1 is minus half and m2 is half. It could also have come from m1 is plus half, m2 is minus half, except that this state is distinctly different from this. They are orthogonal to each other, and therefore there are two different coefficients there, c and d, except that mod c squared plus mod d squared is 1, the same way as mod a squared plus mod b squared equals 1. So the problem now reduces to finding out, to estimating the values of, to determine values of a, b, c and d given these conditions, and given the fact that these states are normalized to 1 and they are orthogonal to each other. The manner in which this is done is straightforward. We know the action of j minus and j plus, the raising and lowering operators on the angular momentum states. J minus is j1 minus plus j2 minus. J minus is the operator acting on the coupled basis, j1 minus on system 1 and j2 minus on system 2. It's clear. And similarly, j plus is j1 plus j2 plus. So let's write this better. J plus is j1 plus j2 plus. The effect is as follows: j plus acting on the state jm is root of j minus m into j plus m plus 1. I have set h cross equals 1 in all these problems, and I have j m plus 1. I am using double braces because these are coupled states, and j minus acting on j m gives me j plus m, j minus m plus 1, j comma m minus 1. j1 minus acting on the state j1 m1 does the same thing. It is j1, or let's start with j1 plus. It is j1 minus m1 times j1 plus m1 plus 1, j1 m1 plus 1. j1 minus acting on the state j1 m1 is j1 plus m1 times j1 minus m1 plus 1 with a minus sign. So this is the way they act. Similarly, j2 acts on the state, the operator j2 plus acts on the state little j2 comma m2, and so on. So given this, I can now do the following. If I used j minus on the state 1 1, apart from the coefficients put down there, I should get the state 1 0. That amounts to doing j1 minus plus j2 minus on the state half half. j1 minus of course acts only on j1 comma m1, and j2 minus acts on j2 comma m2, and so on. And this is how I will be able to estimate, get the values of a and b. So let me do that now. So let's start with 1 comma 1. J minus acting on 1 comma 1 is root of j plus m times j minus m plus 1, which is just root 2 1 comma 0, and j1 minus plus j2 minus acting on half comma half. This state is to be understood as j1 is half, m1 is half, j2 is half, m2 is half. This object is simply going to be j1 acts on this, giving me root of j plus m to j minus m plus 1, and does nothing to the other state, plus J2 minus acts on J2 M2, this is J2, that is M2, this is J1, that is M1, leaving this state alone, untouched, and pulls out a J2 plus M2 times J2 minus M2 plus 1, except that it lowers the M2 value. So, in the first case, the M2 became minus half, the M1 became minus half, and the M2 continued to be half. In the second case, the M1 continues to be half, and the M2 becomes minus half. And therefore, I have 1 0 is 1 by root 2 times half minus half, half half, plus 1 by root 2 half half, half minus half. In other words, I can now fill up this column. I will have the following: 1 1 is half half, 1 0 is 1 by root 2 times half half, half minus half half, plus half minus half, and 1 minus 1 is a stretch case anyway, that is just minus half minus half. So, I have got A and B, and it is clear that A squared plus B squared, each of them being 1 by root 2, A squared plus B squared is 1. 0 0 is orthogonal to 1 0, and this, together with the fact that C squared plus D squared equals 1, without loss of generality, I am choosing C and D to be real values. Otherwise, I would have done mod C squared plus mod D squared. I can choose them to be real because there is a phase, and I am only concerned with the squares, their addition to be 1. And this, together with C squared plus D squared equals 1, since I know A and B, would give me that C is plus or minus 1 by root 2, and correspondingly D is minus or plus 1 by root 2. Either of them is correct. I have to choose a convention, but as it happens, I can write 0 0 as 1 by root 2 times minus half half minus 1 by root 2 times half minus half, 1 by root 2 half minus half, or the other way around. Either is right. A convention has to be used, and a certain convention, once decided upon, must be used throughout the problem. In this case, we do not have any issues on this matter. We can use C to be plus or minus 1 by root 2, and D correspondingly to be minus or plus 1 by root 2. Therefore, I have got the CG coefficients for both the triplet state and the singlet state.